Good morning, students. Am I audible? Am I audible?
Sir, good morning.
Good morning. Okay, ask your friend to join as soon as possible. Okay, where are others? Okay, one more thing I'm going to inform you that some students are there in railway engineering that they didn't attend any class but had given exam for first sessional. Okay, so I'm going to report all this particular student to Dean sir. Okay, it's your for your kind information. So, is there anyone is listening? So please convey the message to that particular student who haven't attended any classes but have given the exam. It's not worth it till now. Fine. So let me tell you, I don't have right now. I don't have the record who have given the sessional exam who haven't attended any single class for railway engineering. Anyway, I'll prepare a report and I'll send it to program coordinator so that he can give to the dean sir. Okay. So so let's start, right? So good morning, students. This is a class of railway engineering professional elective 1. Clear? So we have already completed the first module of railway engineering, and today we are going to discuss about the third class of second module. Third class, fine. So in the first class of second module, first class we have started with wheel axle arrangement of a locomotive. Then in the last class, what you have discussed? Can anyone tell me?
Coning of wheels.
Coning of wheels. Great. So we have discussed about coning of wheels. That means the wheel of rail or train or locomotive, you can say, is of conical shape. Okay. So why this conical shape is provided and how its conical shape is provided is already discussed. What is the slope? Anyone? What is the conical slope? What is the slope of the cone?
So 1/4.
1/20.
1:20.
Yeah, 1/20. Sorry.
Yeah, okay. It's okay. कोई बात नहीं. याद कर लेना अच्छी तरह से, ठीक है? Try to remember the drawing. Drawing is very important. If you can draw the drawing by yourself, put all the component, it will, it's very good for you, right? So we also discuss how to, so that means advantage of coning, disadvantage of coning, right? And we also discuss about how to minimize the disadvantage of coning. How to minimize? Anyone? How can we minimize disadvantages of coning?
Sir, by tickling of wheels.
Right, very good. So by giving tilting of rails. Okay. So by tilting of rails, we can provide, it is able to provide a more contact surface area of rail with wheelbase. Okay. Wheelbase means we are talking about a wheel tread, or you can say rim part. Okay. It's also important to know the basic component of a particular wheel. Okay. The inner wheel face is called what? Tread, right? It is a larger diameter. Okay. So these things already discussed with you. If I have any doubt, you can also ask me or text me. Anyway, so today we are going to discuss about some resistance forces that may act against the movement of a train. Okay, that means particular some force, okay, either mechanical force or some other atmospheric force, or may act against the movement of the train who that reduced or they resist the movement. That means they reduce that speed of the train, you can say. Okay, so we're going to discuss about different factor that effect in the movement of the train. Okay, so I'm going to share my screen now. By the way, I just want to ask right before that right now 12 participants are there. I mean 12 students are attending right now, but as per my register, I think more than 25 students are registered in railway engineering. I think exactly 27 or not. I think 27. Okay, so please, okay, I'll give you some next class or some in WhatsApp also. I give some roll number. So please inform them to do something. Okay, about their attendance. Anyway, so I'll share my screen now. Okay, my screen is visible, right?
Yes, sir.
Okay. Wait a second. Okay. So here you can see we're going to discuss about various resistance and their evolution. Okay, it's not that important, but we need to know the basics of that resistance. What are the resistance force are acting on or against the movement of the train? Okay, so basically, various forces offers resistance to the movement of a train on track. Okay, so this resistance may be the result of the movement of various parts of the locomotive as well as the friction between them. Additional to that, it is maybe due to the irregularities in the track profile or the atmospheric resistance to the train moving at a great speed. That means the overall resistance against the movement of the train we can classify under mainly two head. Okay, one is your mechanical, another one is your atmospheric. Okay, under mechanical resistance you can say friction force is there. Okay, okay, friction maybe uh, between the train, that means between the train parts, because in a particular, if I say train, it consists of a different component, mainly two component. One is your locomotive, the engine part, and the trailing part, that is the wagon. If this is a passenger train, it will be a passenger compartment will be added with the engine or locomotive, or it's a suppose a goods carrying wagon. So we can say goods carrying wagon only. Okay. So whatever it is, so we have two part. One is locomotive, another one is your wagon. Fine. So there's some connection between each and every compartment or each and every wagon and along with your locomotive. Fine. So the various forces offers resistance to the movement of the train on the track. Fine. This resistance may be the result of the movement of the various parts of the locomotive. That means I already told you there are various parts of the locomotive. Okay, because of that friction or resistance offered by that various part, because of the friction between them, they may offer a resistance. Okay, as well as the friction between friction between them. Fine. And the irregularities in track profile. Irregularities means uh, somehow tracks are like this in a curve way. Somehow somewhere in hilly area you have to go up, in downstairs you have to go down. That means there is no one uniform track profile. There is a irregularities of the profile. Okay, so in that particular track, while moving through the track, some force may resistance force may be occur, and which resist the track attractive force, you can say, or train force of the movement. Then atmospheric resistance to the moving train. That means you also know, with increasing in the speed of any vehicle, whether you consider train or bike or a car, you also experience some wind drag acting against the movement of the vehicle. Similarly, even in the movement of the train also, atmospheric resistance also act in opposite direction like wind force. Okay, so it basically it's depend on shape and size of a particular wagon. Okay, that means we have to prepare that circumference, or you can say the shape of a particular wagon in such a way that it can overcome the wind forces or wind drag. Fine. So this is overall. This is the basic summary of various resistance acting against the movement of the train. So likewise, how many of this kind of resistance force are there? Resistance due to frictions is there. Okay, resistance due to friction, then resistance due to wave action. Here you can see resistance due to wave action, then resistance due to wind. Here you can see resistance due to wind, then resistance due to gradient. Here you can see resistance due to gradient, then resistance due to curvature, resistance due to curvature, and at the end resistance due to starting and accelerating. I can summary here. Yeah, resistance due to starting and accelerating. Okay, I'll make it very simple so that you can understand. Okay, so we'll start from here. Resistance due to friction. So basically, friction is divided in two parts. One is internal friction, another one is your external, or you can say the rolling friction. Fine. So resistance due to friction is the resistance offered by the friction between the internal parts of the locomotives and wagon, as well as between the metal surface of the rail and wheel to a train moving at a constant speed. Okay, that means this friction may be between the internal parts of the locomotive and between locomotives and the wagon. I already told you that the locomotive and wagons are connected with some mechanical means. So there must be some friction between that particular joint. Okay, so this is come under internal friction. Okay, and the friction between the rail surface and the wheel of the train. We all know that wheel move along the rail only. Okay, that means the tread part, the rim part of the wheel always in contact with the rail surface, top surface. So there is a possibility of friction. This friction between the rail and the wheel is considered as a rolling friction. Okay. So as a whole, overall, the resistance can be further broken down into following parts. That means the total resistance due to friction can be divided into two parts. One is internal friction, another one is your rolling friction. The internal friction is consequential and to the movement to the various part of the locomotive and wagon. Okay, that means the internal resistance depend on the movement of the various part of the locomotive and wagon. Fine. And the rolling resistance, basically, it is due to the rail wheel interaction on account of the movement of the steel wheel on a steel rail, or both are made of the steel. Okay, so we can give a numerical equation or formula to find out the overall or total resistance due to friction. Okay, so total friction due to friction, total resistance or total frictional resistance is given by the empirical formula this. Okay, let's try to remember this. Okay, we have five formula for that, five numerical equation for that. So R1 represents your total resistance due to friction. Since it is the first resistance we are talking about, that's why 1 is come as a suffix. Okay, so R1 is given as 0.0016 multiplied by W. Okay, where R1 is what? Your frictional resistance. Okay, which is independent of speed. It's very important term. Okay, it is very important. That means the frictional resistance does not depend on the speed of the train. Okay, it's independent of the speed of the train. Fine. Frictional resistance does not depend on speed of the train. Someone is waiting. Okay, we have joined the class right now. Please try to come at time. Okay, it is already 9:40. Fine. So from next class, please be on time. Anyway, so total frictional resistance is given by this empirical formula 0.0016 multiplied W. And where W is what? W is the weight of the train, and which is give in a unit of tons. Okay, this is also important term. W is the weight of the train as overall, okay, locomotive plus wagon, overall train in ton. Okay, even your R1 also come in ton only. The unit of the resistance due to friction also come in ton. Okay, so this is all about your resistance due to friction. Next, we'll discuss about resistance due to wave action. Okay, so resistance due to wave action. So when the train moves with a certain resistance developed due to the wave action in the rail. So I already told you, right, that the track profile of a railway is not a uniform. Okay, so if I give a top view, the the railway track is not always a straight line. It's somehow it is somewhere like this. Okay, I'm giving this. This is a top view. Okay, from sky you can see it like this. Okay, fine. So even if I give a cross-sectional view, even in the hilly area, now I'm giving a cross-section view. Okay, in hilly area, the track must be go up, then at down you have to go down like that. So somehow the track profile is not uniform. Okay, and because of the track profile of this, the wave action of the train generated. Okay, it is not moving in a straight line. Always in a sometimes it is basically in some not always, especially in case of hilly area or uneven area or undulated area, it the wave action come in action. Okay, so resistance due to wave action. So when train moves with a certain speed, a certain resistance developed due to wave action in the rail. Similarly, track irregularities such as longitudinal unevenness, difference in cross levels also offers resistance to the moving train. Okay, we are not till now we haven't discussed about crossing. Okay, so we are not going in that part. Even in the crossing part, that means when two railway, especially in case of some junction, okay, there is a crossing of rail. there is a track, railway track, which are cross to each other. In that area also, uh, when one train is moving from another track to another, that means for one particular gauge, I'm talking about the one particular gauge, when in times of crossing, there are some also wave action occur. Okay, track irregularities also is there. Okay, so there is no such specific method to calculate the wave resistance due to wave action, but you can go through, you can at least theoretically you can go through this empirical formula. Okay, so where R2, you can say R2 equal to 0.00. So R2, you can see your resistance due to wave action, it is 0.00008 WV, where R2 is what? Your resistance due to wave action in ton. Okay, and track irregularities on account of the speed of the train, and W is the weight of the train in ton, and V is the speed of the train in kilometer per hour. So here main point is what? This resistance due to wave action depend on the speed of the train. But here you can see the resistance due to friction. Resistance due to friction does not depend on your the wave action. That means sorry, the resistance due to wave action, resistance due to friction, sorry, resistance due to friction does not depend on your speed of the train. Okay, but the resistance due to wave action, it depends on speed of the train. Here even in the empirical formula also you can see V is there. Okay, but here V is not there. It is independent of the speed of the train. Okay, these things you have to remember this part. Okay, so yeah, V is in kilometer per hour, weight of the train in ton, even the resistance due to wave action also come in ton. Okay, so this is all about your resistance due to wave action. Okay. Okay, so next part is your resistance due to wind. So when a vehicle moves with a speed, a certain resistance develops as vehicle moves to move forward against the wind. Okay, so these things are very logical, and I think you have also experienced that means when you move with a certain speed in any vehicle, whether it is train, a bike, or any car, one may experience a wind drag against the movement of the uh, vehicle. Okay, and if somehow the wind direction is against the train direction, then the resistance due to wind will be increased. Okay, and the magnitude of the resistance due to wind is basically depend on what? Size and shape of the vehicle. Okay, the magnitude of the resistance due to wind is basically depend on size and shape of the vehicle. Depend on size and shape of the vehicle, also in any speed. Okay, the speed is very also important, and the wind direction as well as and its velocity. Okay, these things are the factor which dependence of the wind resistance. That means the magnitude of the resistance due to wind depend on the shape and size of the vehicle, its speed, and the wind direction, and as well as the wind speed. Okay, so this is all about your resistance due to wind. And overall, if you since I already told you that it depends on the shape and size of the vehicle. Okay, so we have two empirical formula. Okay, so here you can see R3. You were also given R3. That means whatever value you can put. Suppose you have this two parameter, you can use this formula. If suppose you have this two parameter, you can use this formula. It's okay, depend on the situation. If you want to calculate the resistance due to wind, okay, acting on a moving train. So here you can see two empirical formula are there. one is this, one is this. Okay, here your in the first formula, this 0.000017 multiplied by A into V2, where A is your exposed area of the vehicle. That means the circumference of the train, outer circumference of the train. Okay, since this wind resistance depend on the shape and size of the vehicle, so we have considered here the exposed area of the vehicle, okay, in meter square, and the velocity, that is V, velocity of the wind, not velocity of the train. V here, V is the velocity of the V2 actually. Okay, V2 is the velocity of the wind in kilometer per hour. Okay, now in the second equation, empirical equation, you can see R3 here, some little bit longer empirical formula is there. Okay, so this parameter multiplied by this coefficient multiplied by weight of the train in ton, and V2. Here V2 is what? Your velocity of the train in kilometer per hour. So there is a difference. Okay, so you can remember this formula and also the parameter. What is A, what is V2 in this formula, what is V2 in this formula. Okay, so be careful about that. Clear? So whenever you are using exposed area as a input parameter, then you have to use velocity of the wind. Okay, since exposed area is related to the wind velocity only, so you have to come together. Now when it comes to weight of the vehicle, if suppose you are giving the weight of the train, then you have to use velocity of the train. Okay, because they are related. Okay, clear? So after this we have a resistance due to gradient and resistance due to curvature and resistance due to starting and accelerating. Okay, so what is the time now? Okay, now I think we can't complete all these things. I'll do one thing. I will skip this thing for now because I need some time to make you understand the resistance due to gradient, resistance due to curvature, and resistance due to accelerating. Let me check whether I can complete or not. I will try. I'll try. So anyway, up to this it is clear, right? Resistance due to friction, resistance due to wave action, and resistance due to wind. Okay. So it is also very not that complicated. Resistance due to gradient. Now we all know that in suppose in hilly area the gradient is higher. Okay. And again after hill crossing the hill you have to go down. Okay. Fine. So when the train moves on a rising gradient, it requires extra effort in order to move against the gravity. Okay. Now here you can see a line diagram of a particular hill. Okay, suppose this is our horizontal surface, this is your actual surface of the earth, which is a hilly area, and just suppose this hilly area or hilly surface making an angle theta with the horizontal. Okay, so this is a line diagram so that you can understand. And suppose this is a train wheel is moving upward and try to move upward, and also it have to carry the wagon along with it. Okay, now compare, if you compare with the horizontal direction, suppose this is a horizontal direction, concentrate here. I'll take a pen. Okay, suppose your horizontal direction like this, suppose your train is moving in this direction, so the weight of the train is directly downward direction. Okay, it is the case of a horizontal movement. Now when it comes to a higher rising gradient, that means a train is moving in upward direction, the resultant component of the weight of the train is acting downward or against the movement of the train. You can see this is your W, original W coming from the center. Okay, but the component of the W, okay, is going in this direction, your against the movement of the direction. That means to move in a rising gradient, the train require extra effort because of the additional component of the W, which is giving a resisting force against the moment of the train. You got this right? I think this kind of drawing is very simple to you. You already got these things in different subject. Line diagram, I'm talking about the line diagram or free force diagram. Okay, so will the velocity of the movement of the train is in this direction. The movement of the train is in this direction, but the weight, the component of the weight, one component of weight is against the direction. So this kind of the additional force acting against the movement of the train. It gives some resistance when it come to rising gradient. But when it come to decreasing gradient, okay, or decline gradient, this become this W component become this component. That means it become additional force. That means it will act as a driving force when it come to decline gradient. But in case of rising gradient, it gives resistance. Fine, it is a basic thing. Okay, so when a train moves on a rising gradient, it requires extra effort in order to move against the gravity as shown in figure. Assuming that the wheel of the weight W is moving on a rising gradient, these things are already discussed here, so we just go through this. Okay, weight of the wheel acting downward here, normal pressure acting. So the resultant force of the train is R4. Okay, this resistance force. Since W, one component of the weight, is acting in this direction, So I think it will be your W, I think sine theta. Okay, I'm not sure, but I'm just giving W sine theta is acting in this direction. So to resist this force, we have to provide one another force like this. This is R4. Here it is written now. R4. And what is R4? R4 is your resistance due to gradient. R4. Okay. Clear? I think this is clear, right? So resistance due to rising gradient R4, which act parallel to OA. Where is OA? OA. This is the plane. Okay. So this R4, the resistance due to gradient, act parallel to this line, to this surface. Okay. So these things I already discussed with you. Just go through the notes. Okay. These things. Okay. Okay. I'll do one thing. Till now, I want to stop now. Next class we'll complete this resistance due to curvature. Fine. And resistance due to starting and accelerating. Fine. So till now, is it clear? Is it clear to you? Any doubt till now? So I'm closing my sharing. Okay, I'm closing my sharing. If you have any doubt, you can ask me. If you don't have any doubt, then I'll just take your attendance. Clear?
Yes, sir.
Okay, so I will stop my recording here. After stopping my recording, I will take your attendance, and if you have any doubt, you can also ask me. Okay, I'm stopping now.